Hello everyone and welcome back to my channel. In this video, we are going to learn about homogeneous and heterogeneous nucleation. So let us restrict ourselves to this solidification phenomena, that is this transformation from liquid to solid. And for this, let us consider this diagram where the first particle of the solid is forming from the liquid. So let's say this is the solid which has formed. So above this you have all liquid. It forms unaided by any surface or defects. As the solid particles form, an interface between the solid and the liquid is created. And therefore, surface energy or interfacial energy is involved here. Right, so this is the first particle of the solid which forms, and this is known as the nucleus when it attains a critical size. Okay, so only when it attains that particular size, it will grow into the solid. If it is below that critical size, then it will be known as an embryo, which is not stable. Okay. So it has to reach that critical size for the nucleus to grow into a solid. So this free energy change that you have here for this particular transformation from liquid to solid, that has two components. One is the surface energy and another is the volume free energy. Okay, that is shown over here in this particular diagram. This part that you see on the upper side, that is the surface energy contribution, and on the lower side you have the volume free energy contribution to this delta G. Okay, and delta GV is the specific volume energy change, that is free energy change per unit volume, right? So if you consider this tiny particle of the solid as a spherical particle, then the surface area would be 4 pi r square, and if gamma be the specific surface energy, that is surface energy per unit area, then the surface area contribution to the free energy change is this 4 pi r square gamma, and the volume free energy contribution is this, where 4 by 3 pi r cube is the volume of that spherical particle, right? And this is the summation of these two, the solid line that you see. Okay, so the maximum that you see over here, that is the size that the particle has to reach for it to be called as a nucleus, which can grow into the solid, right? If it is below this critical size R star, then it will be an embryo, and for it to grow as a nucleus and develop into the solid, it has to reach this critical size, then only it will be called as a nucleus. Okay. So if you now take up these contributions, this is what you would get. Right, as I said, it has two contributions, the volume free energy and the surface energy, right? And since the critical size occurs at the maximum, as you could see, right? If you take the derivative of this delta G with respect to the size, then at this point it will be 0, right? So that's what is shown over here. D delta G by dr is equal to 0, and this is the derivative, 4 pi square delta G plus 8 pi r gamma. That is, if you simply differentiate equation 1 with respect to r, this is what you get. And from here you can derive r star as this minus 2 gamma by delta GV. That is the critical size or the critical radius of the nucleus. And you can also derive the critical free energy change for the nucleus to form. And it will be given by this particular equation over here, right? So this is homogeneous nucleation, where the whole process is mainly controlled by the surface energies, okay? So as long as you have a driving force for this surface to be created, this will continue. So what is different in heterogeneous nucleation? In the heterogeneous nucleation, you have some preferential sites for the nucleus to form, right? It is not going to be uniform anymore, as you have seen for the homogeneous case, right? So the nucleus will tend to form at some preferred sites, such as the mold wall, when you are pouring the liquid metal into the mold. Inclusions, if they are present in the liquid metal as suspended particles. Grain boundaries, right? So these are the sites which can act as the preferred or preferential sites for the first nucleus to form, right? And that is why this is known as heterogeneous nucleation, because now the nuclei will form heterogeneously at such sites rather than forming homogeneously. As shown in this diagram, where theta is the contact angle, and now if you consider this into the free energy change, you would see this additional term in the form of theta will come. So here the nucleation occurs on a surface which could be a defect or the mold wall in case of solidification, right? So this is the diagram which represents that. So this is the surface that we are talking about, on which the nucleus is formed, right? So this could be a defect surface or the mold wall, as I said, okay? So that's what provides a substrate for the first nuclei to form from the liquid phase. And in this case, you will have to look at the surface energies also, because now, these interfaces are there. Apart from the solid liquid interface, there is an additional interface between that heterogeneous surface and the solid nucleus, and also between the surface and the liquid, okay? So we are calling that surface on which the nucleus is forming as interface. indicated by I. Okay. So this is the interface, solid interface on which the solid nucleus is forming, right? And this is the corresponding interfacial energy, gamma IS. Okay. Similarly, this nucleating surface also has an interface with the liquid, so that is IL, and this is the corresponding interfacial energy. And this is the interface between the liquid and the solid, so the corresponding interfacial energy is this one, gamma SL. Okay, and this is the contact angle between the solid and the heterogeneous surface on which it is forming. Okay, theta is that contact angle. So theta can be found out if you take the balance of forces here. Okay, so from this equation you can actually derive the expression for theta. Okay, so it's all about the surface energies here. Theta will also have a role to play on the free energy change. So now if you look at the free energy change for this case, that is delta G heterogeneous, then here also there will be two contributions like how we had before. One of course coming from the volume free energy change, and rest will come from all these surfaces, right? So here in this case the nucleus which is forming is considered to be a spherical cap. So the area is derived based upon this assumption that the nucleus is in the shape of a spherical cap. Okay. So let's say the volume of that is that cap is Vc. Okay. And delta Gv of course is the volume free energy change. So apart from this, you will have the surface energies. Where ASL is the area of this interface here, which is the solid liquid surface. Similarly, this is the area which is here, the heterogeneous surface and the solid, that particular interface. And you can also see the corresponding surface energies. Okay, and here you have another term which is negative. So this is the positive surface energy which is added to it. This is because of that creation of the new surface as we discussed before. But here this particular term you can see is negative, and this area is taken equal to the area of this interface between the solid and the heterogeneous surface on which it is forming. Okay, so this essentially means that the interface formed between the nucleating surface and the nucleus replaces an equivalent area of liquid and the surface interface. Right, which you can see from here, right? So this is the surface which is formed between the solid and the heterogeneous surface, right? And this is formed out of this particular surface which is between the liquid and the heterogeneous surface, right? So an equivalent amount has been replaced when this interface forms, right? An equivalent area is replaced by formation of this interface between the solid and the heterogeneous surface. Now, considering the geometry of this, if you just do a simple geometrical analysis here, you would come across this particular expression for the free energy change. As I said, this can be easily derived by a simple geometry. I am not going to do this here. Maybe you can take this up as an assignment and you can do it yourself. So this particular term actually is similar to the homogeneous nucleation, if you recall. where this indicates a spherical nucleus that we considered before, right? So this SP indicates spherical shape for the nucleus, right? So this is nothing but delta G homogeneous, right? And therefore we can write that delta G heterogeneous is equal to delta G homogeneous multiplied by a factor which depends on the contact angle. So this one we can call as S theta, and therefore delta G heterogeneous becomes equal to delta G homogeneous into S theta, right? So if you plot this S theta as a function of theta, so here you can see when theta is equal to 0, S theta is also 0, right? So you have a point over here. And when theta is equal to 90 degrees, you can see that it is equal to 0.5. S theta is equal to 0.5 when theta is 90. Right? So it will vary like this. And as you could see, when the theta is equal to 180 degree, this becomes, S theta becomes 1. Right? So from here, we also need to calculate what is the energy barrier for the heterogeneous nucleation, that is the critical free energy change for the heterogeneous case. Okay. So following a similar approach of setting the d delta G by dr equal to 0, we can find out delta G star heterogeneous as this. This is delta G star homogeneous. We already know that. And therefore delta G star heterogeneous becomes this. Right? So from here you can see that the energy barrier for the heterogeneous case is much smaller compared to the homogeneous case for all practical values of theta. Okay, because we have seen how h theta varies with theta. Okay, so now if you plot this delta G star heterogeneous by the delta G star homogeneous, as a function of theta, you would see that delta G heterogeneous is much smaller when theta is small, and then it goes to a value of 0.5 when theta is 90 degree, right? So for all practical values of theta, you can see that delta G star heterogeneous is always less than delta G star homogeneous, right? So for small values of theta, the energy barrier for the heterogeneous nucleation will be much lower compared to that for the homogeneous nucleation case, and that is why in nature generally the heterogeneous nucleation is always preferred, because the energy barrier for the heterogeneous nucleation is lower. Okay, so from here you can easily see that delta G heterogeneous is going to be much smaller compared to delta G homogeneous, right? And as a result of that, when you have heterogeneous nucleation sites, more number of nuclei can easily form compared to the homogeneous case, right? So that is how you get a higher nucleation rate also in case of the heterogeneous nucleation. And higher the nucleation rate, lower will be the grain size, and that is how the heterogeneous nucleation leads to a finer grain size in the solidified material. Okay.